The third messenger, a true cosmic visitor. A whisper from the galactic core. It began not with a bang, but with a whisper in the data, a faint streak of light moving too fast, too straight, against the backdrop of Jupiter's stars. On July 1st, 2025, the Atlas telescope in Rio Hurtado, Chile, sent a quiet alert to the Minor Planet Center. "We've found something that doesn't belong." Within hours, astronomers confirmed it. This was no asteroid, no fragment of our solar system. This was 3I/ATLAS, the third known visitor from interstellar space. And unlike the silent, dark enigma of Oumuamua or the distant glow of Borisov, this one was already alive, already breathing, already telling its story in dust and ice. The name that tells a story. Names in astronomy are more than labels. They're histories. 3I/ATLAS carries three truths. 3, the third of its kind. I, for interstellar, a rare designation reserved only for objects proven to originate beyond our sun. Atlas, honoring the global network of telescopes that found it, our planetary sentinels. Before it, there were only two. 1I/Oumuamua, 2017, a mysterious, inert wanderer. 2I/Borisov, 2019, a true comet, but observed with limited tools. Now, in 2025, we have a third, and this time, we're ready. This time, we have Hubble, Webb, and a fleet of planetary explorers watching. This time, we won't just glimpse the messenger. We'll read its letter. Born in another star's cradle. When we trace 3I/ATLAS's path backward through time, it doesn't lead to the Kuiper Belt or the Oort cloud. Instead, its trajectory points towards Sagittarius, the constellation that cradles the center of the Milky Way. For millions, perhaps billions of years, it drifted through the void between stars. It was likely born in a protoplanetary disk around a young star, perhaps similar to our Sun. At some point, gravitational chaos, maybe a close encounter with a giant planet, catapulted it into interstellar exile. It has been sailing ever since, cold, silent, preserved. And now, after eons of darkness, it enters a new star system, not to stay, but to pass through like a cosmic pilgrim. The proof is in the orbit. How do we know it's from outside our solar system? The answer lies in its orbit. Most comets follow elliptical paths, closed loops that bring them back again and again. But 3I/ATLAS? Its path is hyperbolic, a one-way curve that never closes. It approaches the sun, swings around it, and then escapes into deep space, never to return. This shape is only possible if the object is moving faster than the sun's escape velocity. When discovered, it was already traveling at 137,000 miles per hour, 61 kilometers per second, far too fast to be captured by our star's gravity. In orbital mechanics, this is the smoking gun. A hyperbolic trajectory equals interstellar origin. No debate, no doubt. First light. June 14th, 2025. Though officially discovered on July 1st, 3I/ATLAS had already been in our skies for weeks. Archival data from 3 Atlas telescopes and Caltech's Zwicky Transient Facility at Palomar Observatory revealed faint detections as early as June 14, 2025. Back then, it was just a speck, barely visible, moving slowly against the starfield. But now, with its true nature known, those early images are precious. They let scientists reconstruct its full approach, refine its speed, and even model how its activity began as sunlight first warmed its surface. It's like finding the first page of a diary you didn't know existed. Suddenly, the whole story makes more sense. A comet, not a rock. One of the most important questions: is it a comet or an asteroid? The answer came quickly. Telescopes saw a coma, a bright glowing cloud of gas and dust surrounding its nucleus. This is the hallmark of a comet, a dirty snowball of ice, dust, and organics that sublimates as it nears the sun. This is crucial. Comets preserve primordial chemistry. Asteroids tell us about rock. Comets tell us about the ingredients of life. 3I/ATLAS is not just a visitor, it's a time capsule from another star system. Hubble's portrait, a teardrop in the dark. On July 21, 2025, when 3I/ATLAS was 277 million miles from Earth, the Hubble Space Telescope turned its eye toward it. What it saw was breathtaking, a teardrop-shaped cocoon of blue-tinged dust swirling around a solid core. This is the coma, the glowing atmosphere of a comet created when ices sublimate into gas, dragging dust particles into space. But the most poetic detail? The background stars are streaked. Why? Because Hubble wasn't tracking the stars, it was tracking the comet. As 3I/ATLAS raced along its hyperbolic path, Hubble moved with it, keeping the comet sharp while the stars blurred into short, diagonal lines. It's a visual metaphor. The universe is still, but the traveler is in motion. Size, from skyscraper to small mountain. How big is 3I/ATLAS? As of August 20, 2025, the Hubble Space Telescope has narrowed it down. Minimum size, 1,444 feet, 440 meters across, about the height of the Empire State Building. Maximum size, 3.5 miles, 5.6 kilometers, roughly the width of Manhattan. That's a wide range, but it's expected. Comets are tricky. Their nuclei are hidden beneath veils of gas and dust, making direct measurement difficult. Hubble's sharp vision helps, but even it can't see through the coma completely. Still, even at the smallest estimate, 3I/ATLAS carries enough ice to fill thousands of Olympic pools. And that ice isn't just water, it likely contains carbon monoxide, methane, ammonia, and possibly complex organic molecules. Each of those compounds is a clue, a fingerprint, a sentence in the language of another star. Webb listens in infrared while Hubble sees dust. Webb hears chemistry. On August 6, 2025, NASA's James Webb Space Telescope pointed its near-infrared spectrograph, NIRSpec, at 3I/ATLAS. Unlike visible light, infrared reveals the molecular fingerprints of gases: water, CO, CO2, methane, even potential organics. A preprint of early results is already circulating among scientists. Though full analysis takes time, Webb's data will tell us what ices dominate its nucleus. Are its chemical ratios similar to solar system comets? Does it carry the same prebiotic ingredients that may have seeded life on Earth? If the answer is yes, it suggests life's building blocks are universal. If no, it means our cosmic cradle is unique. Either way, we learn something profound. SpaceX joins the hunt. From August 7th to 15th, 2025, another NASA mission joined the watch. SpaceX, the spectrophotometer for the history of the universe, epoch of ionization and ices explorer. Though designed to map the entire sky for ices in star-forming regions, SpaceX can also pivot to study bright, nearby targets like 3I/ATLAS. Its strength? Broad spectral coverage. It can detect dozens of ices and molecules at once. A research note is already in preparation. Together with Webb and Hubble, SpaceX helps build a complete chemical inventory of this interstellar visitor. A solar system united in observation. What's truly remarkable isn't just what we're seeing, but who is watching. NASA has activated a fleet of assets, turning the entire inner solar system into an observatory. Hubble and Webb, from Earth orbit, TESS and SWIFT, scanning for outbursts and UV emissions, Perseverance and Curiosity. Mars rovers pointing their cameras skyward, Mars Reconnaissance Orbiter, capturing wide-field views from orbit, Lucy and Psyche, en route to asteroids, but still tracking Europa Clipper and JUICE, future ocean world explorers, already collecting data, Parker Solar Probe and Punch, studying how the comet interacts with solar wind, SOHO, ESA/NASA, watching from the Sun-Earth-L 1 point. This is unprecedented coordination. Never before have so many missions focused on a single interstellar object. It's as if the solar system itself is leaning in to listen,